started. It's my pleasure to introduce our speakers today. Shuang, Principal Engineer, and Baxter, Durham, Senior Engineer from Westinghouse Electric Company. They are also our alumni.
Yeah.
NC State. Shuang graduated with master's degree from Nuclear Engineering Department here in North Carolina State University in December 2008.
That's right. That's Dr. Terinsky right here.
Okay. And since then, he's worked at Westinghouse Electric Company on various technical and commercial projects. He's currently responsible for Taiwan Power Company in capacity of principal engineer and project manager. Baxter graduated with bachelor degree from our department in December 2010, and since then he worked at Westinghouse as a core design engineer. Currently, he is senior design engineer responsible for Excel Energy. Let's welcome our speakers.
All right, well, it's a pleasure to be here. Thank you, everyone, for coming, first of all. Today, we have an exciting seminar for you today. We're going to talk about a completely different type of fuel assembly that's been used previously that combines two different kinds of burnable absorbers. And as you'll see in the following slides, the purpose of doing that is to have the best parts of both types of burnable absorber in the core to extend the life from 18 to about 24 months for one single cycle. All right, and to get us started off, Baxter will do the first half and I'll do the second half.
Good evening, everyone. So the title of our presentation is Hybrid IFBA Gad Assembly Designs for Long PWR Cycles. Like Shuang said, this is a combination of two different burnable absorber methods that we've used previously in plants in the same assembly lattice, which is something that we haven't looked at before. So today, most US PWR plants operate in 18-month cycles, which are quite a bit longer than they were originally designed and operated for. And going forward, we're even interested in longer cycles such as 24-month plus, so 2 years of operation. So these very long cycles require burnable absorbers, both to control the moderator temperature coefficient and also to control power distribution. So some of the examples of burnable absorbers that we use commonly at Westinghouse are this list as follows that I'll go over. The first one is zirconium diboride IFBA. So what this is, if you're not familiar with it, it's actually a zirconium diboride coating on the fuel pellet itself. So this is integral to the fuel rod, so you have your pellet, then a coating of zirconium diboride, and that goes into the cladding. This has the best fuel economics due to complete burnout at EOC. Since it's a zirconium diboride coating, by the end of the operating cycle, it's completely been burned out of your core. This also has a minimal impact on local power distribution when compared to the effects of similar burnable absorber options such as gadolinium or our wet annular burnable absorbers. Because it is a coating, it does offer good power suppression at beginning of cycle, but you don't end up with a whole lot of residual negative reactivity as the core burns. One of the other common integral absorbers that we use is gadolinium. So this is mixed in with the uranium as gadolinium oxide. And one of the key features about this one is, in comparison to IFBA, few burnable absorber rods are required for the same amount of hold down. And it also has a much slower burnout, which provides good control over the entirety of the cycle. So these guys burn faster, these guys burn slower, but you need fewer of them to hold down your reactivity at beginning of cycle. One of the other things that we use commonly is a wet annular burnable absorber, or a WABA rod. So this is a discrete burnable absorber. Whereas the first two are integral in the fuel rod, these are actually rod assemblies that go in the guide tubes of the fuel lattice. So these have very slow burnout as well, which provides good control over the cycle. But some of the limitations of the WABA is it's limited to assemblies that will not contain control rods. Because if your control rods need to insert, you can't put something under those. And another challenge that another challenge of using these discrete burnable absorbers is during cycle outages, since they're not integral to the fuel, it provides some challenges when you're performing your fuel shuffles and loading your core, because you need to take the discrete burnable absorber out, move things around, and then put it back in. One of the other previously used integral absorbers is IFBA. This is a little bit less common nowadays, but it offers cross-section spectral characteristics for good MTC control. It's similar in nature to gadolinium. And it also has a slow burnout profile over the course of the cycle. For Westinghouse PWR designs, the zirconium diboride IFBA, which I'll just refer to as IFBA for the rest of the presentation, has actually been the preferred choice for customers for 18-month cycles. So, as I mentioned before, we're looking at extending cycle lifetimes even further. So, in particular, we're looking at very long 24-month plus cycles. And since we are looking at these very long cycles, consideration regarding the choice of burnable absorber becomes more important. So, in order to hold down the reactivity needed to reach this long cycle length, a significant increase in the number of burnable absorbers is required just for that early cycle hold down. But because it has to last so long, there's also a longer duration of the cycle that hold down has to occur for. One of the limitations that we have currently is there is an NRC limit on peak rod burnup of 62,000 megawatt days per MTU. And that provides incentive for us as core designers to reduce the core and local power peaking in order to meet the burnup requirements. So for 24-month cycles in high power density Westinghouse plants, 4 loops are the major example of those. The IFBA may not be sufficient alone in order to meet all of the hold down requirements for the duration of 24 months. It's good for 18 months, but it might not have quite as much hold down as we need in order to reach 24. However, due to substantial fuel cost considerations, there's a great incentive to use IFBA over other burnable absorber types, since it is a coating on the pellet itself and it has complete burnout. It ends up being more economic than loading the core with other burnable absorber types. So there's an incentive for us to look at using IFBA as our main burnable absorber choice and augmenting it with some of our other options. So the first thing that we did in looking at how we would change the loading and loading multiple different burnable absorbers into an assembly lattice is we performed assembly lattice studies. So we took just an assembly lattice, particularly for a 17 by 17 Westinghouse RFA fuel assembly, and we used our Paragon lattice code in order to study the effects of loading different burnable absorbers into the assembly. So we came up with a set of approximate burnable absorber requirements, so requirements that these designs needed to meet in order for us to consider them in an actual loading pattern. The first one is that the assembly had to maintain excess reactivity less than 20% delta K, and what this does is it shows that we would have a relatively good chance of meeting MTC limits if we loaded a core full of assemblies of this nature. Another thing that we were looking at is minimizing the residual burnable absorber worth at 30,000 megawatt days per MTU for optimal fuel economics. And why we chose 30,000 megawatt days per MTU is for a 24-month cycle, this would be the relative discharge burnup of our feed batch. So we want to make sure that we have the least amount left over at the end so that we have residual penalty is the least going into the next cycle when we're shuffling them back in. And then the last thing that we were looking at is minimizing local power peaking in order to maximize core operating margin. This is always something that we're looking at for safety reasons. So these were the assembly lattices that we looked at as part of the study. The first one contained 104 IFBA pins. So the IFBA pins are the orange colored pins, and those are fuel rods that are coated in the fuel pellets that are coated in the IFBA. The second assembly lattice type that we looked at was a 64 IFBA 24 WABA design. So you can see that there are 64 IFBA locations, and then there's also a WABA rod in each of the 24 RCCA guide thimble locations. The third type that we looked at was 100 IFBA rods augmented by 8 Gad rods. So again, the orange squares represent IFBA locations, whereas the black squares represent where we placed our Gad rods. And for this study in particular, we used 8% Gad. So the enrichment of your Gad is very important. The higher the enrichment, the stronger the burnable absorber. And then our final lattice that we looked at for this study was an assembly with just 20 Gad locations, as indicated by the black squares. So here are the results of the assembly lattice calculations. As you can see from the black dotted line, this is our no burnable absorber, so it's our comparison case. And then you can see that the IFBA, as far as K infinity, like I said earlier, IFBA might not be strong enough alone in order for us to meet our MTC limits. You can see that right here. So the delta K over 1 for IFBA is much higher than the other options that we looked at. For the 20 Gad, the 64 IFBA and 24 WABA, and the 100 IFBA and Gad assemblies, all of the reactivities were relatively the same, with the maximums all being right around the time of IFBA burnout. From a rod power perspective, however, you can see that the 20 Gad rods had much higher power throughout, and that's just due to how black the absorber is. So since the Gad is a much stronger burnable absorber, it's pushing power to all the other locations, meaning we're getting higher rod powers in the assembly. And for the rest of our burnable absorbers, particularly the 64 IFBA 24 WABA and the 100 IFBA 8 Gad, the power peaking profile was relatively the same for those two options, with the 100 IFBA having the lowest. Again, this comes back to what I was saying on the first slide, where IFBA just by itself has a relatively small local power impact when compared to our other options. So when using IFBA augmented by some of these other absorbers, we get that hold down that I showed in this slide, but we still end up keeping the peaking below what we would see using something like just 20 Gad rods. So this is a slide that provides a summary of our assembly lattice study. So for the IFBA provides the lowest residual burnable absorber penalty at end of cycle, and it also has the lowest power peaking, but it can't meet our hold down requirements for the cycle. Remember when I said we set this up, we established that 20% delta K was going to be our limit for us to say we could meet our MTC. Well, IFBA by itself for 24 months ended up exceeding the 20% delta K. The other options met, but whenever you take into account reactivity and power peaking considerations, it suggests that our 100 IFBA with 8 gadolinium rods is our best option to move forward with, because whereas the max K infinity of the IFBA WABA and the 100 IFBA 8 Gad design are relatively similar, you can see that there is a much there's a big difference between the EOC residual reactivity penalty whenever you're using the 24 WABA rods as compared to the 8 Gad rods. And I should state, when I say end of cycle residual, it's for the assembly lattice depleted out to 32,000 megawatt days per MTU. So what this does is essentially models a fresh assembly for the duration of a single operating cycle. So here's what we proposed: an IFBA Gad hybrid assembly. The proposed assembly concept would contain mostly IFBA, and those IFBA rods would be augmented by a handful of gadolinium rods. One thing to note is that whenever I say a hybrid IFBA Gad assembly, the IFBA and Gad rods are in separate fuel pins. So if you have Gad in one fuel pin location, you're not also putting IFBA there. It's either a Gad pin, an IFBA pin, or a fully enriched non-burnable absorber pin. Using this configuration is nice because there's actually no lead test program required, methods development, manufacturing changes, or even major licensing that would be necessary for implementation, because all of the parts have been used before and we have a lot of operating experience with them. So we're not creating something new, we're just taking the tools that we have and creating a new configuration. And I will turn it over to Shuang for the second half of the presentation.
All right, so Baxter showed you what an individual assembly can do in the core in terms of K infinity and the different types of burnable absorber, how much delta K it's worth, and why we chose IFBA and Gad, right? And so now what we're going to do is we're going to take the choice that we made based on the information that we had, and we're going to put them in an actual core, and we're going to run it, and we're going to see not what the K infinity is, but what the K effective is in the actual core, right? And so what we did here is that we used a for-loop core, and here are the parameters of the for-loop core that we looked at. 193 assemblies, Westinghouse for-looper, of course. Core power, cycle length of 680 days, which is approximately 24 months, and a peak rod burnup limit of 62,000 gigawatt days per MTU. Right, so this is what our core design looked like for the 24-month cycle. And you'll notice here that in a 24-month cycle, we end up having some feeds on the periphery. Typically, that's not done, but with 24 months, in order to have enough reactivity in the core to go the full 24 months, that's unavoidable. So this is the IFBA loading pattern design, and as you can see, the red assemblies are the feeds, and everything else is the once burns. Typically, in a shorter cycle, you'd have 3 regions in the core: feed, once burns, and twice burns. But here, again, because you're loading so many assemblies, about half the core in this case, you have no twice burned assemblies. But that's okay, because once you look at the discharge burnup, which is the number of megawatt days you're getting per metric ton of uranium, for a 24-month study, it's not actually that bad if you average it over the full region size. So this is what the 24-month IFBA Gad core loading pattern looks like. Again, very similar, checkerboarded interior with a few feeds out in the periphery, and once burned assemblies out in the corners here. This is the 24-month Gad-only loading pattern. Like we were talking about before, the disadvantage of a Gad-only loading pattern is that the Gad, because it's mixed into each individual fuel pellet, what happens is that it actually displaces uranium, right? And uranium is the thing that's actually making power, of course, so you have less uranium in the core, which means you need more assemblies to actually make this happen, to make the 24-month cycle happen in terms of reactivity. So how do these cores actually behave over the course of the 24 months? Well, here's what we see here. 24-month critical boron concentrations. You see that with IFBA Gad, the results are actually very close to IFBA WABA, which is really what we were going for here, right? Gad only has this sort of an effect. There's no IFBA peak here. And the point of that IFBA peak is that at the beginning of the cycle, the IFBA is actually burning out faster than the core is losing reactivity. And so the critical boron concentration needed to maintain criticality actually goes up. Kind of weird, right? But Gad doesn't have that problem because it burns out very slowly, right? So the rate at which the Gad burns out and the rate at which the core loses reactivity is about the same as each other in the beginning of life anyway. So power peaking, right? So here we see that the IFBA Gad and IFBA WABA it actually outperforms the Gad only, with lower FQ here than the Gad only and the IFBA WABA. Right? So the IFBA Gad here is the solid red line. The IFBA Gad is the solid purple line. So again, the point that these graphs are trying to make is that IFBA Gad together has all the advantages of Gad and IFBA put together. You don't have the reactivity defect that Gad has, the residual reactivity defect anyway, but it still provides a higher level of hold down than IFBA only. Okay, so as you can see from this table, which is a tabular representation of the graphs that we just saw, IFBA Gad has superior capabilities compared to the IFBA WABA, IFBA only, and Gad only. So again, we're combining the best aspects of IFBA, IFBA WABA, and Gad only into a hybrid assembly that meets all of our criteria for a 24-month cycle. So fuel economics, IFBA Gad actually saves you money. And the reason why it ends up saving you money is, again, because gadolinium, what happens is it ends up displacing uranium. So you need to increase the enrichment of everything else that doesn't have the gadolinium in the assembly, so that equates to higher ore costs, higher conversion costs, higher assembly costs if you need more assemblies. All the costs go up. So over an equilibrium cycle, the Gad cost is about 1.2% higher than the IFBA Gad pattern, which is actually 0.3% cheaper than the reference IFBA Gad pattern. So the conclusions are that all three configurations can meet 24-month design requirements. That's something that can happen. But if you want to meet it well, and if you want to control the peaking, and you want to do it cheaply, IFBA Gad is really the way to go. And again, as Baxter mentioned earlier, the other benefit of having IFBA Gad is that licensing concerns are addressed, because again, we're using two things that have already been licensed, and we're putting them together in one fuel assembly. So now, we've actually implemented this at a plant in the United States. No LTA required, because again, we're not doing anything new per se here. We're innovating something based on designs that we already have. And it's expected that this design will be used in the future for 24-month cycles. And that's it. That's IFBA Gad. Does anyone have any questions?
So questions, comments?
Can you put the economic one table back up?
Sure.
Okay. So when Indian Point was doing this, which I assume maybe your customer doing it, because they have a law that says they have to do it. They never wanted to do it because basically the penalty in the fuel cycle cost, remember 2n over n plus 1 fuel cycle cost, the fact that you're using less regions. In those days, the economics were, given the price of uranium SWUs and replacement power costs, it just didn't make sense to run 24-month cycles. Has that changed?
Well, when we did the analysis, when we look at the discharge burnups, in terms of how many megawatt days you're getting per MTU for an 18-month cycle versus a 24-month cycle, it was such that it was comparable. It was enough so that they decided to go with it in the end.
Okay, but I'm just looking here. I mean, you got 8.69 for the 18-month cycle. I'm talking about going from 18 to 24.
Okay.
And you got 9.93. So you're taking very big hit in fuel cycle costs. And the question always is that hit offset by the reduction in replacement power cost?
Right.
Because you're only refueling, you're
Right,
refueling less frequently.
Once every 24 months,
Yeah.
right.
Yeah, and it obviously depends on whatever cost assumptions you use for uranium and SWU.
Certainly it does.
And then it obviously, the overall economics will be dependent on replacement power cost.
Yep.
Mind if I throw in
Sure.
Yeah.
Go ahead.
So actually, in particular for the customer that's operating with this right now, since the U.S. fleet is getting to the end of its operating license lifetime, what has been done for a lot of these plants is they're looking at how many outages they have until the end of license lifetime,
Okay.
and how many outages could be saved by going to 24-month cycles as opposed to 18 months, since the outages are very expensive for the plants. And that was one of the main drivers for that particular utility going to 24-month cycles.
Okay, so I would say it's more than replacement power, you're
Yes.
correct. It's replacement power plus the cost of an outage, which is millions of bucks
Yes.
on it. And for that particular utility outage, actually overall economic, that fuel cycle cost penalty was more than offset by the savings that they get in the reduced replacement power plus the cost of less outages.
Okay.
Other questions, comments? So is that means that now for pressurized water systems, we're moving to cycles?
Well, as Dr. Turinsky had indicated, it really depends on the economics of each particular plant, how much an outage costs, how much replacement power costs, and how many outages they have left until end of life.
But currently 18 months is kind of standard.
It is standard for 3 loopers, and 4 loopers.
Yeah, and that was based on economics. That
Mhm.
was really the minimum when they shifted to 18 months, probably what, 15 years ago or 20 years ago.
Right. I mean, as you can see, the batch sizes are much larger, right? And you have to throw out enough assemblies at a lower discharge burnup. That, of course, one way that some utilities have considered this is you can have an 18-month cycle in one unit, a 24-month cycle into the other unit, and you can feed the assemblies that aren't burned quite as much into the 18-month cycle to be used as burned fuel. That way you can raise the overall batch discharge, so you get more energy out of each megaton of uranium. So that's an idea that's been thrown around. Yes, sir.
So if you were to try to use a custom configuration, one that hadn't already been verified and validated, what would that cost? How much did you save by using these already currently approved versions for your configuration?
While licensing something through the NRC is always a little bit of a question mark, it depends on how many RAIs you have, and typically that process takes months, if not years.
Plus you need some lead test assemblies.
Right.
Which would have set you back
Exactly.
6-7 years.
That's a really good point. LTAs, of course, you put it in a plant and you need to burn it for a few cycles after that, and 18 months plus outages plus another 18 months.
So one thing to note about this is it's not completely removed from the licensing process. So even though we didn't have to do lead test assemblies or additional safety analyses for it in particular, we did have to license the use of both of these burnable absorber types in the same lattice, since that was a design change that hadn't been used at that plant before. So there's still some cost associated with licensing when implementing this. However, that cost is much less than if we were to use something that we had never used before.
Right. ATF, for example, advanced,
Uranium silicide.
exactly, and the chromium-plated stuff. Accident-tolerant fuel, industry is moving towards that, and one of the things that is kind of holding it back is that we need to do LTAs in different plants to make sure that it performs well under real conditions.
I have a question. So, I missed a point. So, why is the residual burnable absorber a problem at the end of cycle?
Well, because gadolinium isn't completely burned; it's still there. Mm-hmm. Whereas the zirconium dioxide, it will burn off completely.
But why don't you want that? What's the problem? So you have your fuel. It's got the final burn up, so you're going to dispose of it, right? So
right.
Why does it matter if you still have gadolinium in it or not?
Well, it matters because your fuel is less reactive and you can make less power from it before.
Okay.
Right.
So it's not for the post processing.
Right. It's for because you're trying to make power out of it, and your critical boron concentration will get to 10 or so, and you can't dilute anymore. So you can't get any more power out of the reactor.
Okay. I thought it was for.
No, the results that we saw that were shown for the assembly lattice designs were actually for a fresh assembly operating for one cycle. So you would expect that fuel to be reloaded into the second cycle, so you want it to be as reactive as possible.
Right.
I understand.
Any other questions? We're happy to answer anything you guys have.
More questions, comments?
Yes, sir.
Now, because you are reloading for 24 months, that means if you just go to the core like 2 or 3 times, that for one fuel assembly, that will mean like 24 times 3.
Well, in a 24-month cycle, typically we discharge after just 2 cycles, right? Because there's not enough room in the core to put it in there again. Because you have to load over half the core, or else there won't be enough reactivity to get the core to the 24 months.
Your discharge burnup limit.
Right.
Determining what you got to load.
Exactly. And as we said before, the discharge burnup limit is 62,000 for American plants. But that's a pin burnup limit, right? So you got to look at how your assembly is being burned through the cycle. Sometimes the assembly might only be at 55 and the pin is already at 62. So that's a core design constraint there that has to be investigated during a 24-month implementation. Yes, sir.
Silicide fuels.
Mm-hmm.
Are they getting used for burnable poison?
I don't know the answer to that. but
Someone better know the answer.
someone better know. That's right. That's right. The advantages of silicide are clear, though, right? The higher temperatures and all that. There's a lot you can do with it.
Other comments?